Okay, Jim. Yep.
All right. Good afternoon. Good afternoon, folks. I'm Jim Bell. I'm a professor here in SESE, and I am delighted to introduce our speaker, Professor Evgenya Shkolnik, for our SESE Colloquium today. First, are there any announcements anybody has to make? SESE announcements? No? We're good? Okay, and Rick, hopefully the folks online can hear us okay. Say yes, you're good. Okay, cool. Very excited to learn about the work that Evgenya is doing here in SESE with colleagues internationally. She comes to us from a background with physics and mathematics degree from Dalhousie University in Nova Scotia, master's and PhD from University of British Columbia. Well, you got around in Canada, east to west. And she worked as a postdoc at University of Hawaii and at Carnegie DTM. Went to Lowell as assistant tenure track assistant astronomer and came to us in 2015. Seems like yesterday. 2015 came to CC and is now an associate professor here in our department and also associate director of ASU's Interplanetary Initiative, which is where we perhaps have collaborated most. The effort that Michael Crow and Lindy Elkins-Tanton are cross-campus bringing people together to think about the future of humans in space. That's super exciting. Also a visiting professor at Harvard and an honors faculty here in the Barrett's Honors College. You're going to hear a lot about what Evgenya does with UV work on stars and planets. One of the cool things she does is SPARCS, Star Planet Activity Research CubeSat, great acronym. That is one of these new family of tiny little spacecraft like LunaMap that did a successful flyby of the moon recently, and it's great to see you be one of the pioneers here in small-sat science-focused small sats, and that's we're going to learn about that. I'm going to relearn what hazmat means during the talk because I've forgotten. You've already told me. And then we'll also hear about UV scope, ultraviolet spectroscopic characterization of planets and their environments. So this is going to be super exciting. And we're delighted to have you. Thank you for making time to be with us today. And let's welcome Evgenya Shkolnik.
You okay? Yeah. Thank you for that nice introduction, Jim. And it's so great to see everyone here and all the folks online whom I can't see, but I feel your presence and support. So what I just wanted to say that because this is a hybrid mode, I'd been experimenting when doing fully virtual talks with breaking a couple of times for questions. So I think today we're going to experiment with taking questions partway through, just once, and then at the end again. Okay, so we're going to do kind of science and then some technology. All right, with a break. So if you feel like an urgent science question, your time will come sooner than you expect. All right, so thank you, everyone. So as Jim said, I am here representing three of my teams, the HAZMAT team, which stands for the Habitable Zones and M-Dwarf Activity Across Time. This is a large GALAX and HST Hubble Space Telescope program. And SPARCS and UV Scope, as Jim mentioned, there are two missions. SPARCS is a small CubeSat mission that's already funded by NASA, and UV Scope is a mid-X astrophysics mission, which will be proposed in the next mid-X round. And so I'll tell you a little bit about both of those. But since I know we have quite the interdisciplinary crowd here, I wanted to catch everyone up on what we have learned from 3 decades of planet hunting. Okay, but some of you might not even know that we've really only been successful at planet hunting outside of our solar system, so exoplanets, for about 3 decades. And here's what I think are the 4 most incredible facts. First of all, exoplanets are everywhere. So what we now know, thanks to the Kepler mission, is that planets actually outnumber stars in our galaxy, which is incredible, right? This is not something that you typically read in textbooks. Does everyone know this? Did everyone know this before I just said it? That planets, you knew this? Thank you. Planets outnumber stars in our galaxy. This is an incredible fact. Like our entire worldview has to shift with this fact. And I asked some students yesterday. I gave a class yesterday, and very few people raised their hands. So this is clearly not permeated our society yet. So I'm just going to keep saying it until everyone knows it, because I think it's incredible. Of the 5,000 so far that have been confirmed, they're extremely diverse. They are more diverse than the 8 planets in our own solar system. So if you plot them on a mass radius relationship or whatever parameters you want, they span a much larger parameter space. So far of these 5,000, we have about 25 or so confirmed habitable zone planets, rocky planets. HZ is going to be habitable zone. You'll see that throughout the talk. And then if you work out the statistics, right, knowing that on average, every star has a planet, but there's about 25% of these planets are rocky planets orbiting, 25% of the planets orbiting low mass stars, which are the dominant stars in our galaxy. You can work out the numbers, and it turns out that just in our one galaxy, there are about 70 billion rocky planets in their habitable zones. That's a lot, right? And so I can't tell you that they're habitable. I can't even tell you that they're potentially, or I can't even tell you that they're inhabited. But if all other conditions are right, then we can, then it would be a very exciting place to look. And so the habitable zone, very crudely, right, is the place where if all other conditions were correct and liquid water was on the surface and the atmosphere still existed, right, that you could have a habitable planet. And around our solar system, it's at roughly 1 AU, where we so comfortably sit. But if you take a much hotter star, right, your habitable zone moves further out because you want to be far away from the fire, right? You don't want to be too close to the fire. But if you are cooler, like a low mass star, which we also call an M star or a K star, these are stars that are cooler and smaller than the sun, their habitable zones come closer, right? You have to get closer to the fire to stay warm. And so these small planets, these cooler stars, make up about 75% of all the stars in our galaxy, right? So when someone says the sun is an average star, it's not. The sun is not an average star. It's these low mass stars are the actual average stars. And so in addition to being the most numerous, right, they also therefore host the most rocky habitable zone planets. So if you want to understand, as I do, my guiding question of my entire career is, Nuri just asked me this today with the student lunch, so thank you for reminding me of it, is what is the distribution of habitable environments in our galaxy? That's my guiding question. And so pretty much everything I do relates to that. And so therefore, I have to start caring about M stars, because that's where the most habitable environments probably are. There's another benefit to M stars, is that because they're smaller, the transit signal as a planet occults it, cuts across, produces a bigger signal, which means the signal to noise of whatever observation you're looking for, either it's the planet detection itself or looking for transmission spectroscopy. I'll show you a plot in a minute to explain that. It means that they're actually a favorable place to look for planets and to look for planets with atmospheres that we want to characterize. And let me see, can you guys see here's my mouse, right? So here's just showing you where these M stars and K stars lie relative to the sun on mass and luminosity plot. So here they are, they span 3 orders of magnitude in luminosity. So they're actually kind of quite a wide range of types of stars, which is why we separate them out into early M stars and late M stars, because they are fundamentally different stars. We just call them all M stars, which is, we're traditionalists in astronomy, so we're never going to get away from it. So I just have to keep pointing it out. And our very nearest neighbor, Proxima Centauri, so the star closest to our solar system, is one of these M stars that is much smaller, much cooler, and has only 0.2% of the sun's luminosity. Right? Now, I will also tell you, hopefully you have read about this in the news in the last few years, but it's also the host of a habitable zone rocky planet. Now, you should not be surprised, because I told you those planets are everywhere. So, of course, our next door neighbor will have its own rocky planet in the habitable zone. But because this star is so much cooler, the orbital period of this planet is 11 days, and it's only about 10 stellar radii away. And we'll get back to why this is important and potentially challenging. And so these M stars are also then favorable to measure the atmospheres, the constituents of the atmospheres. And this is the I would say, the leading technique right now. There are other ways to look for atmospheric constituents, or the chemical composition of atmospheres. But this is the leading way, through transmission spectroscopy. And that means that you're essentially just looking at the planet as it cuts in front of the star, and the atmosphere is backlit by the star, and then you see the imprint of the atmosphere, of the chemical. So going back to habitability, really, I mean, I think lots of people in this room work on habitability, perhaps from different angles, right? And really, we have to think about it holistically. We have to think about it from the planet properties and the star properties. And this is very much a big giant mess, right? Like, there's so many ways we need to address this problem. My group has been working on it from the stellar property side, trying to understand what is the star doing, and how is that activity in multiple forms affecting the planet and the planet's atmosphere and its the atmosphere and its potential, not only to have life, but also the potential to detect life if it's there. And the star plays a big role in that too. And so mostly what I do with my group is we focus on the ultraviolet. So just to make sure we're all caught up on the wavelength terminology here, is that we look at the ionizing radiation, so the ultraviolet, which is the shorter wavelengths, the higher energy, which is right about here. I focus on, you'll hear me talk about the near UV, the far UV, and the extreme UV. These are just going in order of energy. And these are the ones that, even though the stars are very faint at these wavelengths, right? They very few. There's literally 1 million red photons to every UV photon in an M star, which is why we call them red dwarfs. You might have heard that expression as well. But not every wavelength is the same. These are the ones that are doing the damage. And so we need to study these. Whereas, however, right, the vast majority of stellar and exoplanet observations are done at the optical and in the infrared wavelengths. So most people focus on infrared optical for a whole host of reasons. There's lots of amazing science to be done there, but the UV is generally neglected for a variety of reasons, mostly because the stars are very faint and there are very few instruments that we have. Pretty much it's just the Hubble Space Telescope that can observe in the ultraviolet right now, and its ultraviolet capabilities are fading. So this is why we focus on the ultraviolet. So I put this picture up again that you saw on the first slide, because I now want you to think about stars, not just as the yellow balls that you think about when you see the sun, right, or see images of the sun, but think about them in the UV, because this is our sun in the UV. In the extreme ultraviolet, it's an image taken from a NASA spacecraft called SDO, the Solar Dynamics Observatory, taken during the last Venus eclipse, and Venus transit, I should say. And this is kind of the imagery I want you to have. So next I'm going to go in through, this is kind of the outline of the rest of my talk, is we'll talk a bit more about why the UV matters for exoplanetary systems, what we've learned thus far about them using the existing instrumentation, and then you'll see how we've hit up with the limits with the existing instrumentation, and have therefore been forced into building our own missions to answer some of these really fundamental questions that we won't get to with any existing instrumentation. Okay, so as I said, we now know about 5,000 confirmed exoplanets. The whole exoplanet field has shifted from planet hunting into planet characterization, right? We now are only looking for planets that we can characterize. Isn't that remarkable? It's a total shift in our field. And so really the big questions in exoplanets now is, how do planets form and evolve? What are they made of? And of course, the are we alone question, which is what drives many of us. And in fact, UV observations, UV data, and the impact from the star of these high energy photons is really a really key component to answering all of these questions. And the reason for that is that these are energetic and they penetrate the planet's atmosphere and they impact the surface all the way up. And so this is just to show you that the highest energy ones are absorbed in the uppermost atmosphere this is an example of a terrestrial planet. And the far UV, so these are now the lower energy, but still powerful UV wavelengths from 100 to 200 nanometers penetrate in the middle atmosphere, also called the upper atmosphere. Like I said, terminology is always a challenge for us. And the NUV can penetrate down to the lower atmosphere, and that's where a lot of photochemical challenges can happen. Now, so our team is working mostly now in the UV, but we're also moving into looking for particles. from these other stars. And there's been no conclusive observations of particles of coronal mass ejections, for example, from other stars, but we know that our sun does it. So other stars must do it as well. And we know that that impacts our planets and it must impact exoplanets as well. So I'll talk a little bit more about that shortly. But we're now kind of, as a group, bringing particles, which I actually call like the P word because no one really wants to talk about it because we really don't know how to do it. But we're trying to make an effort in that direction. All right, so back to the sun and then comparing it to Proxima Centauri. So here, this is of course a beautiful image of the solar eclipse, but if you in your mind can now shrink it down to be Proxima Centauri, our nearest M-dwarf neighbor, and here I've plotted its habitable zone terrestrial planet to scale, okay? So it's now about 10 stellar radii away, and you can see that this planet is exposed to a very different environment than we are at our comfortable 1 astronomical unit, right? It is dealing with many more particles and many more UV photons than we have to. And these have serious planetary consequences for the planet from the star. So first of all, you can have atmospheric heating and escape as from the EUV. You actually can evaporate the entire planet or strip the entire planet due to these high energy photons. You can have photochemistry and photodissociation happen due to the far UV and the near UV wavelengths. And of course, both these things impact surface habitability and also impact our detectability of any potential biosignatures. The UV causes so much trouble, and actually there are mechanisms, chemical pathways that produce both false positives and false negatives of biosignatures. So, so we have to work all that out, right? We have to work out. So you can't really, no matter what you detect in the planet atmosphere, you cannot interpret that that spectrum until you understand its UV context. That's just the fundamental truth of it. And then just to show you about if this kind of star was going to have a coronal mass ejection, so this is another example from the sun, right? Then you're actually now impacting the planet with huge amounts of high energy particles now. And this is work that Nuri Park, who's here, is a student here working with myself and Everett Schock. And he's dealing with a lot of solar data so that he can then map coronal mass ejections with far UV flares as a mechanism to try and develop a new way of detecting this, detecting CMEs, coronal mass ejections, and other stars. So when Nuri is ready with his plots, he can come give his own talk. So I'll leave his plots, but he is getting great results with real correlations that we can now start hopefully soon applying to other statistics. All right, so again, this is the real sun doing the real thing and doing its thing. And the sun, remember, is less active than typical M stars. M stars flare more than the sun. So what we try to do now through these 3 programs, Hazmat, Sparks, and UV Scope, is to figure out how much energy is really being dumped, how is it doing across all planet time scales from the time of formation throughout its evolution, and how does it affect the planet in such a way that we can interpret planetary spectrum. All right, how are we doing? Does anyone have a burning question now before we go on? Yeah. I'm sorry, why we can't do it? What? In UV wavelengths? Oh, in radio. Oh, people are trying.
You'll need to repeat
I
the
think
question.
you say that we do observations in optical and wavelengths, sorry, optical wavelengths and infrared, but not in radio. People are really trying hard to do it in radio, actually. There's a big effort to do it in radio. And for the science case for the radio observations is to detect magnetic fields more directly than other mechanisms. And also to observe the particles, if we could observe CMEs also in the radio. So we have a big effort to do that as well. So no, the radio is great. I'm not dissing the radio. I love the radio. Okay.
There's another question here.
Oh, yeah.
Can you do it this way?
You mentioned some of the challenges about working in the UV and how that can impact habitability in sort of a more negative manner. But I was recently hearing about some ideas around maybe UV, a certain level of UV radiation being necessary for
Yes.
like origin of life. How does
That is
like
true.
has there been some definition of
The range that's
the
needed.
range of good UV?
Yeah, yeah. I've had conversations with people, people at Harvard who are actually doing the experiments, trying to figure out what is the minimum amount of UV, and they don't think it's that much. So they're actually not so worried that it's that much. More people are worried that it's too much, but there is a sweet spot. Yeah, that's a great question. Thanks. All right, keep rocking here. Okay, so now I'm going to tell you about the HAZMAT program. This is the habitable zones and M-dwarf activity across time. It's now the HAZCAT program too. For those of you who know my former graduate student, Tyler Ritchie-Yowell, her PhD was to do a similar kind of project, but now focusing on the K stars rather than the M stars, because the community was starting to get nervous that M stars flare too frequently. So we started thinking, well, maybe K stars are the sweet spot for habitability. And it's turning out they're actually more wild than we expected also. So this is what Tyler has been working on in her time here. So what we did for the HAZMAT program is we took archive data from GALEX. This is now a no longer functioning NASA UV mission, but it left us with a really nice archive, and we had new HST observations, so spectroscopy. So essentially the strategy there is to look at a bunch of M stars and K stars as a function of age, so we can map how the ultraviolet emission changes with age. So we know then what is happening to the planet throughout its entire life. And we've been well supported, thankfully, for this program. We've had over 200 HST orbits for this, a couple of large programs stitched together. And so it's been really good and really important, especially because HST is so far our only way of doing this. So here's just one example. This is the first time we published HAZMAT 1 paper. We're up to HAZMAT 9 now, but the HAZMAT 1 paper, myself and colleague Travis Barman from U of A, we did this evolutionary study using GALEX data where we can now take a whole sample, so each of these points is actually a median of a bunch of points, like 20 or 30 at a given age. But at least now we can start saying numerically and statistically what the planet at the time of formation, in this case, in the early days, what's happening at disk dispersal and giant planet formation times, what it's actually exposed to. So then people who model this will now have accurate numbers. What we can also then say what's happening during terrestrial planet formation in the primordial atmosphere. And then the Earth is on its secondary atmosphere. So if this happens to exoplanets like Earth, then what is happening in this particular evolutionary stage? And if the secondary atmosphere survives these M dwarfs, which we can get back to in a minute, and I don't have an answer for you yet, JWST will actually give us some information as to whether or not atmospheres will survive around these M stars in the first place. But if it does survive, then you can assess what the conditions for life might be on such a planet. Yeah. I'm sorry. It's the UV emission from the star for early M stars as a function of age. FJ is the J band flux. It's the ratio of the FUV flux, of the UV flux in the near UV and the far UV to the J band flux. Because when we did the study, we didn't have distances. Okay, the J band is an infrared. This is great. This is great. Well, this is why I wrote UV emission, so people wouldn't get caught up in the details, but the people who want the details will get the details. Okay, it's an infrared band. It's just how it's an infrared band, so we can, when you don't have a distance to something, you can put things on the same scale by normalizing to some other wavelength that doesn't vary. Thank you for asking. Call me out on any of it, Larry. Okay. Anyone else have a question about this or anything else? Okay. So that was the first study, but now with the HAZMAT 5 paper, Tyler led this program where she compared what we had done for the early M stars, but now for the late M stars. So these are the smaller M stars, and to the K stars. And this red line shows you what. So now I'm plotting. Okay, I'm going to go back. These are now different units, but it's still UV emission. So maybe it doesn't matter what the numbers are, but it's UV emission now on the planet in the habitable zone. right? As a function of age still on the log-log plot. It's now the far UV, and it's actually because now we have distances, we don't have to normalize anymore to the J-band flux. We actually can measure the true energy and put it onto the planet. So now we have real units. Wait, ergs per centimeter squared per second. Okay. What this teaches you is that the late M's, the smallest ones, just like Proxima Centauri, stay active for a very long time, much longer than our sun. This is kind of a schematic of what our sun would look like. So you get much more emission for hundreds of millions of years, and then it starts to decline. But at all points in the habitable zone, there is a lot more UV emission in these low mass stars than for the sun. Now, in addition, this is just what we call the quiescent, the regular, day-to-day emission. But but one thing we've been learning is that flares, which that previous plot does not capture, is actually quite intense. So, so here's just an example from Galax where you see an M star flare by 10 magnitudes, which for those of you who don't like to think in magnitudes is a factor of 9,000. Just pops right just like that. And we saw that also in our HST data. Here's a light curve from combined spectrum where you see the normalized flux. So it's kind of unitless at this point over time. And we see that a flare that increased by a factor of 200 in 200 seconds. It's currently holds the record as the strongest flare detected by HST. So much so that HST no longer lets us observe these kinds of flares because they're worried we're going to fry their detectors. So in fact, now there is no way to observe late nearby M stars because they worried that they're going to flare something. Here's another example. This is Proxima Centauri, one of our favorite targets that I talk about lots and lots. And you can see here that it increased in the ultraviolet by 14,000. Okay, 14,000 in one flare in 5 seconds. That exact same flare was caught simultaneously with TESS in the optical, and it only increased by a factor of 10. So what that tells you is that we can monitor these things in the optical as much as we want, but it's not actually telling us what's really happening in the ultraviolet. And James Jackman, who is here, a postdoc in my group, he's doing a lot of work in trying to figure out ways that we can predict what's going on in the ultraviolet using optical data, because really we don't have enough UV space telescopes to do this. Okay, so what we ultimately want is what we call a flare frequency distribution. So the frequency of the flares as a function of energy is a nice power law, like many things in nature. And what you see up here is that the Haas flare, right, which anchors this orange line for the young stars, tells us that young low mass stars are truly much more energetic. They do this every day. They have a super flare every day. A super flare is defined by a flare that's stronger than anything ever observed on the sun. And you can see where the sun would roughly lie. Okay, but there's a lot of energetic flares that we don't know anything about. So these are what happens to this plot? Clearly you can't have infinite energy forever. So we want to know what's happening on the once per day, once per month, once per year part of this plot. How energetic do these go? All right, this is kind of the goal. This is the goal of what I'm getting to next. We want to monitor these stars for a long time, something that is impossible to do with HST or with any other spacecraft in the UV right now. And this is where we're going next. I'm going to talk about Sparks next because this is what Sparks is going to do. But I'm just going to pause for a little science question or two, if you have. Yeah. It's a great question. We didn't
Hang
know
on one sec. We just need to get the questions on the microphone because there's people listening offsite there.
Thank you.
Why would a star flare more in the UV than in the optical?
We're not totally sure exactly, but it's telling us something about the physics of flares, right? So it could be that you have a flare high up, say in the corona, and then you have energy dumping back onto the photosphere. And so there, most of the energy is really put out already in the X-ray and the UV. And by the time you get down to the photosphere, there's actually not much there. And so you're not really heating the photosphere as much. That's probably something that could be happening. But I think knowing the ratios of this kind of flare flux will teach us a lot more about flare physics. Oh, why do small stars flare more than there's more energy? Because they have stronger magnetic fields. more of their surface is covered in magnetic. It's all about magnetic fields. Bigger is not always better. I don't know. Well, they're small. Okay, then we're going to stellar structure, right? So one thing that low mass stars have is deeper convection zones than the sun. So the sun's convection zone takes up about its outer 30%. These low mass stars, the lowest ones, like Proxima Centauri, are fully convective. There's no radiative zone. So people are working hard to understand the magnetic field generation in a fully convective star, how it actually does it. But the measurements are such that you could get hundreds of Gauss, kilogauss on some of the smallest stuff, things that we really do not see in sun-like stars. But it all stems from magnetic phenomena. Thank you for that question. Okay. Yeah. Oh, Amanda.
Yeah, this is just to clarify. So this sort of picture here, where you have this kind of fluctuation of the UV energy, if you're doing a transit or trying to do spectroscopy on the atmosphere of a planet, so this is important. Is that
100%?
Okay? So does it affect the quantities or the specific species that you can identify, or both?
Both. Dealing with stellar activity in all transit data has become a sore point, because especially as you're trying, especially the things with JWST, and you're looking for smaller and smaller planets, your signals are smaller and smaller. And if your star is doing this, right, you're going to have a hard time, exactly as you say, teasing out the planetary signature. And so there's a lot of effort going into now to characterizing all the stellar variability at all wavelengths, even at JWST wavelengths in the infrared. It's not going to be quite as high, but it still happens. So teasing out how the star contaminates your signal is a big part of our research effort. The whole community, not just me.
We have one question from online. So
Yeah.
over the years, as the UV emissions of a star become less and less, what's happening to the star?
It's slowing down. So it's becoming less and less because it is tied to its rotation. So when a star is first born, it typically rotates much more quickly than it does as it ages. So as it ages, it slows down. Again, a magnetic. It's all about magnetic fields. It slows down, and therefore it has less magnetic energy, because it's a phenomenon that has to do with rotation and the interaction, the rotation of the internal structure relative to the outside, to the rate. Okay, I don't want to get into too many details, but it's about the rotation. So as a star gets older, it rotates more slowly and therefore emits less in the UV because of lower magnetic energy. Okay, that's a good question. All right, so now we're going to talk about sparks pretty quickly. So since I took questions in the middle, I think I'm allowed, right, to go a little past 4:45 or 4:15.
The answer is yes.
Okay. So, well, let's just talk about sparks here. So this sparks is a CubeSat. It's going to be, it's a CubeSat that's currently funded by NASA. And we are in the process now of collecting all our parts. We're getting a spacecraft from Blue Canyon Technologies, a camera from JPL, and we're building the optical bench, and our telescope is already here in the basement, and we're going to put it all together right here in this building, right downstairs. It's happening right now. It's at a very exciting stage in its development. So it's a 6U CubeSat, which means it's about this big. I liken it often to a family-sized Cheerios box. If your family eats a lot of Cheerios, it's going to orbit the sun in a sun-synchronous orbit so that we can have uninterrupted observations. So we can really stare at about 20 stars for up to a month each. And we're going to observe both in the near UV and the far UV. And so it's essentially this is one of the beautiful things about small satellites. You can do a dedicated experiment really well. Something that you can't do with HST, because no one's going to give us a month to stare at one star with HST. In fact, Proxima Centauri, that program that we had led by Meredith McGregor, that is the longest observing stare HST has ever done on an M star, and it was 36 hours. And we want to do 30 days. Right? So you can see that we're just probing a whole different parameter space. This is our team. I've highlighted all our ASU people. So this is really very heavily ASU led, ASU developed, ASU built, ASU operated eventually when it's up in space. These are the papers. You can follow up on all the science and the technology if you're interested in this. Let's try and speed things up a little bit. Also, we have a couple of undergrads that are working on this from the Interplanetary Initiative Lab, and I just want to give a shout out to the II that has supported a lot of this work along with SESE. So we're very grateful, and Danny Jacobs, whom you know is a professor here, and SESE is always looking for new undergrads to come join the lab. So if you're interested, here's the link, and it's great fun. It seems like a party every time I walk in there. So if you're interested in getting your hands dirty with some hardware for small satellites, that's your place. I think some people love these. I'm gonna skip this for the sake of time. Also with JPL 3 in the camera, and they have some really great technology. So Sparks has 2 missions. It has a science mission to observe these low mass stars, but it also has a technology mission, and that's to demonstrate these new detectors that have been developed at JPL. And once that works on Sparks and is demonstrated there to work, then NASA is very excited about using them for the next bigger missions, like bigger UV explorers, or even the next Habitable Worlds Observatory, which would be the next flagship that we're already working on. So this has an important programmatic value for NASA. And so, of course, the next question is, when will Sparks fly? Well, we'll be ready for launch in mid of 2024 is the goal. But of course, it's launch dependent. When you're a small satellite, you don't get your own rockets. You have to essentially hitchhike a ride. And so we haven't yet been identified as to which launch we will go with. So you can, plan to wait a few months. And then lastly, in the post-Sparks era, we're thinking about now not just monitoring the stars, but monitoring the planets in the ultraviolet. So doing that transmission spectroscopy that I showed you about, but now not just not in optical and infrared wavelengths, but doing it in the ultraviolet. There's lots of diagnostic power there that we have not really probed with HST. HST has definitely shown us that there's lots to learn, but there's just not enough time and not enough wavelength coverage with HST to do it. So we are putting together a concept called UV scope, the ultraviolet spectroscopic characterization of planets and their environments. This is our team here. It includes Michael Line, one of our local favorite astronomers. And the idea here's this image that you've seen again. The idea is to probe each of these layers of the atmosphere for hundreds of planets. So not just the stars, we're talking about also the planets now. If we look at the exosphere, we can look for escaping Lyman alpha, so looking for hydrogen escaping off the planet, and that tells us something about mass loss of these planets, how much of this high energy radiation really impacting the planet. We can study this upper atmosphere, and that tells us about clouds and turbulence in the upper atmosphere. And clouds is a big issue for astronomers because it impacts our observations at other wavelengths. And even though we will not be able to probe the very low level, the very lowest part of an atmosphere here, because the photons do not actually penetrate very deep, this is best probed at infrared wavelengths. But as I said at the very beginning, if you don't have the UV context, you won't be able to interpret your infrared or optical observations. And so we would be providing the UV observations of the host stars for these terrestrial planets that people will be studying at other wavelengths. And also this didn't make it yet into the science thing, but I think we're going to also be able to do CMEs, coronal mass ejections, with this instrument. It's very versatile. And so I'm very excited to build a new science for this one with CME. We're working on that. Like I said, the observations are going to be transmission spectroscopy, and it just shows you kind of where we are here, complementing JWST and Ariel, which is an ESA mission. And we're going to observe small planets, large planets, and their planet hosts across a wide range, not just M stars and K stars. We're going to do all of them, because you'll have a dedicated mission. This is one of the values of building something that's truly dedicated to a specific topic. So the current design is to have full wavelength coverage. This is really what's really exciting about UV scope. It's something you can't do with anything else. In addition to the time domain and the time coverage, we really can get all the way from Lyman alpha, so from 1200 angstroms, all the way to the optical in one snapshot. And this is just an example of our simulated spectra. It'll be of medium resolution, and we'll use the same high quantum efficiency detectors that we're now demonstrating on Sparks. So you see the thread. We're going to get Sparks to work. We're going to show that these detectors work fabulously, and then we're going to put it into bigger missions. So thanks to Ball Aerospace, who's our partner for this, and made this lovely, beautiful, beautiful rendering of what UV scope will look like. Okay, perfectly. To conclude, let me just give you kind of the big picture of how I've spent the last few years and how I'm going to spend the next few years. And that is to understand GALAX HST UV data, right? Build Sparks and UV scope with our fabulous teams, really, really dedicated teams. These are not big teams, but they're super dedicated. And observe the stars and the stellar flares and the planets and measure photoevaporation and measure composition. Then build the new stellar atmosphere models in order to help the modeling community be able to understand what the impacts are of this kind of stellar environment, to really look at the whole system, not just the planet, which is really how we've been kind of stuck for a few years. And then combine that with the actual observations from optical and infrared that are coming, right? They're happening now already with JWST and with the future observatories as well, and even from the ground. From GMT, which ASU is a part of, GMT will have a big role to play in a transmission spectroscopy in the optical from the ground. So I'll just leave you with the fact that next time you look up into the sky, that it's no longer just stars, right? It's all stellar systems. But then think about it, what's really going on in the UV. Okay, I'm done. Thank you. So I stuck to time. I was good. Yes, Larry. J-band comes from the Two-Mass Observatory down into southern Tucson.
I can never remember HJK, whatever.
JHK. Yeah.
You mentioned, so the UV scope, you mentioned you want to probe degassing by looking at Lyman alpha.
Yeah.
How many rocky planets in the habitable zone of low mass stars do you think have hydrogen atmospheres?
That particular experiment would not be done for the Earths. It'll be done for the sub-Neptunes and the super Earths. And the science case there, I didn't have time to talk about it, but it turns out this is actually a really cool. Another cool thing that Kepler discovered is that small planets come in two sizes typically, right? We have the sub-Neptunes and the super Earths with a big gap in the middle. And we don't know why that is. And the evaporating atmospheres is the leading theory right now. So we'll be testing that theory.
Cool.
Thank you.
Okay, this again, another question of clarification. What species do you think you're going to detect in these atmospheres? I mean, what can you detect, at those wavelengths?
Yeah, good question. We can detect in the planet atmosphere. So there's the Lyman alpha, so it's hydrogen. Then there's in the bigger planet, depends on the planet, right? In the bigger planets, we could detect silicon oxide, iron oxide. Let me see, I had a few examples. I don't think I have a spectrum handy. So here I show magnesium, iron, and silicon oxide, at least, and then some hydrogen and some of in other ones. Those are the main ones. The reason why these are labeled here is because those are the main ones that tell us about cloud formation.
So what about something like CO2 or sulfur species? Are they in that range? I don't know the answer to that. Probably should, but I don't.
I don't know. I don't know.
I thought they were could be in the UV. Anyway, I'll look it up.
It could be. That'd be great. Thanks.
Hi, great talk, Evgenia. I was wondering, so you've chosen 20 stars to kind of monitor with Sparks. Were those 20 stars chosen for convenience, or is there something special about the stars that you're hoping to glean?
Yeah, great question. I didn't talk at all about our target list. Both. The answer is both. They're close enough, so they're bright enough that we can do with a 9-centimeter telescope, but they were chosen for distribution in age, because fundamentally we need to understand the history of any planet, not just what it's doing today, right? Not just what its host star is doing today. We need to understand the history. So therefore, doing a statistical experiment of looking at a few young stars, a few middle-aged stars, and a few old stars. So we can do that same kind of mapping, but now with longer time baselines.
There's a couple comments online. First of all, Summer Starfield says UV scope can be used for stars too. I think you were using it.
Yep.
Yep. And Dan Vanderberg says wonderful presentation. And Samantha, with the CubeSat mission, what are you hoping to find from looking at stars at longer time periods?
For the CubeSat mission?
Yeah.
We're hoping to get the strongest, rarest flares. There are going to be whoppers out there that we expect, if that power law continues, that will be that we can't observe another way. And in fact, when we first proposed sparks, we didn't really realize how strong these M dwarf flares can be. And in fact, because, like I said, HST is nervous that these flares are going to damage their detectors, we started getting nervous. And so Tahina, who's here, who's works on our project, he coded up this amazing thing, dynamic exposure control, so that you could, so if a star just starts growing, you can shrink the exposure time so you don't saturate your detector, which is very clever. Great job on that. So that's exactly, that's what we're looking for, is these big flares primarily.
I have a very quick question. Maybe I missed it, but what's the motivation of using the sun synchronous orbit?
Yeah, no, it's a good question. It's so that you can stare without Earth eclipses at one star for a long time. So for most of the orbit around the sun, you can not be occulted by the Earth. So right now, the Hubble Space Telescope is pretty low in low Earth orbit, and you only can observe for about 40 to 50 minutes per 90-minute orbit. Whereas here, you'd be higher up, you'd have your solar panels always facing the sun, so you could also be charging all the time, and you can look out into deep space for longer periods of time without the Earth getting in the way.
Another quick online of are the ages of the stars to be probed by sparks variable? So the stars you're
ages
doing,
variable?
are their ages variable?
Yes, the target list for sparks consists of young stars, middle-aged stars, and old stars. So we designed it to have variable ages.
You said that
Oh, there you are.
you said that the low mass stars are the most numerous in the universe, and then you also said that the definition is very like wide range. Is that why they're so numerous, or is it because of some intrinsic thing about being lower mass that allows them to survive?
The answer is both those things. So yes, they span a large range of just the way we classify them, but they also live forever. They don't go through a supernova phase. They pretty much never die out. So they last forever. So they end up filling the galaxy essentially. So I think both are true. And also there could be a star formation. Another component is star formation, right? So the mechanism of star formation produces fewer big things, right? And more small things, which is also something that happens in many aspects of astrophysics as well.
I have another one.
Even citation. Yeah.
Can Chandra observe any of your target stars to look for X-ray flares?
About 3 of them, I think, Chandra and XMM, which is another X-ray.
Oh, right.
Yeah, mission. Yeah, the young stars are the flariest of stars. If that's not a word, it's going to be soon.
Works for me.
So yes, there's what we call classic flare stars: AUMIC, AD Leo, DS Leo, maybe one more that are on our target list because they've been so well observed at many wavelengths. So we can make that comparison. But even then, you wouldn't get a month even of X-ray time. No.
Okay, so Evgenya, you got me thinking about habitability and small, low mass stars. And I guess my current from this take home is that given their flariness,
Starting already.
they don't seem like they're going to be good places for things to grow and to live and grow.
Yeah, people are really worried about it. I remain agnostic. And I'll tell you why. Because we're not sure what we're not sure what the particles are doing. And that's a big mystery, which is why we're really moving in that direction. Because it's in order to strip a complete an atmosphere, it's typically requires the heating for the photons, but then the stripping from the particles. And it is unclear whether or not just because a star flares more, that more particles are being ejected. That is not a clear statement. So I don't know. Then you can also, to go back to a conversation we were having at Snacks out there, we also don't know anything about the magnetic fields of these planets, which is where the radio comes back, where we're trying, why we're pushing. And by we, I don't just mean me, of course. This is a whole community effort. These are all really, really big questions. But the community is pushing towards detecting more magnetic fields on exoplanets. So far, we've only done, actually from my group, 4 hot Jupiters. We don't have conclusive evidence of magnetic fields on small planets at all. So, so that's why I remain agnostic. I don't think we have enough information. It is cause for concern, but we have to probe other things.
Yeah, and I'll remind Steve Ruff that we have a number of environments in our own solar system well beyond the habitable zone that are potentially habitable. Right? Mike, maybe you sort of answered my question, though. I was going to ask if you have do you have a way in these measurements, either from UV scope or sparks, to detect magnetic fields in planets around small stars?
It's a good question. There is one way that is an extension of the method that I've been using with my group for the last 20 years, which is the magnetic interaction between the planet and the host star. And if you have magnetic reconnection between the stellar field and the planet field, you can produce hotspots on the star. So yes, we could search for hotspots that are generated as the planet orbits around the star in the ultraviolet. And it's definitely in the ancillary science case for UV scope, but it is not a driving science case. We're not going to affect the design in any way because of that. It's kind of one of these things that will come for free because of just the sheer amount of monitoring that will happen. Yes, like the IO flux tube mechanism. Yeah.
So when UV scope is operational and you're getting a bunch of atmosphere data from planets, that is limited in some sense that it's looking at UV and you can't get into the lower atmosphere. I'm wondering if from the data you are able to get, will you be able to kind of paint a picture about the chemistry that's happening on the planet, or is that just a little bit too far into the interpretation to be able to do that based on what you think you'll get?
What we can do is feed the models. That's what we can do for the low mass planets. So all the stellar observations and the stellar models will feed into the planet models, and then you can pull out what you're saying. So there is a step. It's not directly, because we can't directly measure the atmosphere of a transiting Earth atmosphere, right? Earth-sized atmosphere. But we can provide the information that the modelers need in order to analyze what they do see at other wavelengths. The atmospheres that we will directly be probing would be of bigger planets, like super Earths. Two Earth radii are bigger. It's just the little ones that have little thin atmospheres like ours that are going to be too hard. All good? Great. Thank you.